o'clock, so I think we'll be ready to start. So I want to thank everyone for braving the weather to come out and join us today. Should be a very exciting presentation on astronomy and the solar eclipse. We've been looking forward to this for a while, so it's going to be next week. And again, it's always lovely to see everyone here. So again, I want to thank everyone for coming out. The library always appreciates everyone's support for our programs. So I'd like to introduce Tom Stugmyer first. He's been our city councilman since 2016. He chairs a couple committees as well as serving on some others. You might know him as an air personality on Wadsworth Community Radio, and he also does a lot of background work with that, with production and everything like that. And then lastly, he has a bachelor's degree in physics, astronomy, and mathematics from Mount Union University, which explains why he's a little bit of an expert on this subject. So, once again, thanks for coming out. And again, I'd like to introduce Tom Stugmyer.
All right. Thank you. All right, well, thanks for coming out to this evening here, even with the possible threatening weather. It looks like it kind of missed us and everything, so that's good. Appreciate that. What we'll do here with the program here is I'll just talk a little bit about everything about the eclipse, whether it's some history. We'll start out talking about the different kind of eclipses and a lot of the different history and things like that. Then we'll get into some of the mechanics and visuals, and then at the end, or toward the end of the eclipse part of it, I had planned on talking a little bit about some of the equipment, some of the telescopes and things like that, because in some of my other presentations, there have been some people said, well, you know, if I want to get into the hobby, what should I look for? So I thought, well, and initially, the library had said sometimes the programs they like them to be an hour or two, a little bit longer, and I thought, well, I'd put myself to sleep if I talked that long about the eclipse. So I figured that after we do the eclipse, and if there's no questions or whatever, I can talk a little bit about some equipment too. So we'll go ahead and get what's that?
Is it possible to turn a few of the lights?
I think they were. I don't know if they.
Check with the library.
Yeah, I think he had the ones up here underneath off. So I think that's all they were going to turn off. So to get started here, of course, the eclipse is next Monday, April the 8th, and the times on there, those aren't Bible verses, those are the times of the eclipse. Totality starts at 3:13:49 and ends at 3:16:47, 2 minutes 58 seconds, basically 3 minutes of totality here in Wadsworth. You'll see different times. If somebody posted things for Wadsworth, I'll explain that later. They're all correct, because if I ran those times for the village of St. Edward down here and I run them for up at Blooming Acres, there's a 3-second difference. Those are the gazebo. There's a 3-second difference there. So the two different types of eclipses are, let me back up here for a second. The really unique thing about eclipses that we have here, we're going to explain these two different types. In the sky, the moon, perspective-wise, looks to be the exact same size as the sun. It's the same exact size. And that, throughout this whole presentation, is going to just put out some of the most unique things that we've got to observe and use eclipses for. So, now the moon orbits the Earth in an elliptical pattern. So there's sometimes it's closer to the sun, sometimes it's further away from the sun. Now the fact that it's about almost the same exact size, I mean, if like right here by you, I can't see anybody in the background, but if I move back a little bit, 3 people appear. So the fact that it's the same size and just a little bit of the difference in the orbit of the Earth changes the eclipse. So here we go. Get rid of that. Last October, there was an annular eclipse down in the southwestern part of the United States, and that is where the moon is a little bit further away from the Earth, and so it is smaller, so it doesn't cover up the entire surface of the sun. So you'll see the ring of fire around that. That's just like the Johnny Cash was singing, the Ring of Fire. That's where that came from. But and that's what you'll see. The entire face of the sun is not covered. Now, we're going to be fortunate. Next Monday, we will have the total eclipse because, again, the Earth or the Moon is closer to the Earth, so it's going to be bigger and cover the Sun. And in an illustration here, you can see here at the top. Now, there's there's the annular eclipse, and you can see where that focus point is way out here beyond the Earth. And then you can see in the relative, you can see where the Earth is closer. And now the exact point is focused right on the Earth, and so that's where you have your total. Now the partial eclipse look the same either way. You don't see anything much different there. So you won't notice it on a partial, but on a total eclipse, that's the difference. It's literally not rocket science. It's just the fact that, I mean, if I held a quarter up close to my eye, everybody would disappear. And that's all it is. It's just strictly blocking the light. Talk about this a little bit more later too when I do the filters. During a solar eclipse, there is nothing unsafe or nothing different about the light that is hitting the Earth or your eyes. It's not like the ozone is thinner and it's allowing anything, anything like that coming in. It's the same light that you see now. There's nothing different. It's just blocked. It's just that people, all the precautions is nobody's going out in the, like this afternoon and standing there and staring at the sun. There's no reason to do that. And but everybody will go to look at the eclipse or whatever. And if you, especially if you're using any kind of optical equipment, you'll fry your retina immediately. So, but again, the light is no more unsafe during an eclipse than any other time. So this is the path of the eclipse across. So I keep hitting the wrong button here instead of so as the eclipse comes across the United States here, that is the path. And of course, Ohio is right here. And I'll talk about this a little bit later here, but this is a little easy to see. You see down here where the path is a little more round, or the totality is round. Know how it's oblong up here? Okay. I'll demonstrate this a little bit later, but the Earth is round. As you take a flashlight and shine it direct, as you go angle-wise, it instead of being round, it changes. That's why that path of totality is different, because it's up higher on the surface of the sun. That will affect all the times as well during the eclipse. The eclipse starts down here. I hit the wrong button again. Here we go. Eclipse starts in the equator runs right across here, so that the eclipse starts down in the South Pacific, runs up to the North Atlantic. That's just almost exactly a 5-hour period. The longest part of the eclipse is in Mexico. It is 4 hours and 28 seconds. The longest an eclipse can ever be is 7.5 minutes. This is a little bit longer. The one that came across the United States, and I'll have a slide on that later. Back in 2017, that was I think only the longest part of totality there was 2 minutes. So this one's a little bit longer again, because the Earth the Moon is a little bit closer to the Earth this time, so it's covered for a longer period of time. But again, and why the curved path? Well, everything, because the Earth is rotating underneath the eclipse. So you've got the shadow down there, but the Earth is rotating underneath it, and then as the Moon's in its path, it creates the arc. And again, the arc also is because of the curvature of the Earth. You can see down in the southern part, it's curved this way because the Earth's down this way, and up above the equator, it's going the other direction. So that is the path. And then what we have here, I'm going to talk a little bit about eclipse cycles. And this was kind of neat that the 2001 and 2025 slide here showed all this. Eclipses do repeat themselves. They're called Saros cycles, S-A-R-O-S. They're 18 years, 11 days, and 8 hours. And so every 18 years, an eclipse will repeat itself. So you can see right here that this is the one next Monday. or 18 years ago, the same path was in Europe. You can see now. The one that was in 2017 you don't see on here because 18 years before that was 1999, or was so it's not on here. But you can see down here, this was repeated here in the southern hemisphere. You have all of these in here that were repeated every 18 years apart. Now the serocycles, what they are is whether I'd run out of knowledge talking about it, or you'd fall asleep first, it would be a race. But there's about 40 to 42 different serocycles, eclipse cycles, at any one time. They'll start down, when they start, they'll start like in the southern hemisphere, and they're partials, and then as everything moves around and the moon orbits the Earth in a 5-degree plane. And it tilts like a record wobbling, and so it takes every 18 years that cycle repeats. But after they run their course, and again they'll start like in the southern hemisphere, and they'll go up here in the central part, and you see some of the older ones up in the northern part of the hemisphere. They'll run between 1,200 and 1,500 years, and then they're done. And they start right back up again. And so like I said, well, why isn't this, why isn't it easy to predict an eclipse? Well, it is if you know what serocycle you're looking at. And so again, there's, like I said, about 40 to 42 running at any one time. These are the eclipses that will cross the United States in the 21st century. The one in 2017, you can see, came across this way, and this is the one next Monday here, intersecting down here in southern Illinois. Now, the last eclipse in Ohio was in 1806. Talk about it a little bit later. It was called Tecumseh's eclipse, 1806, and the next one that crosses Ohio will be in 2099. Which will come here. Now, and again, 75 years from now, anybody, maybe even if they're 30 years old, could be 100, or somebody, a 20-year-old gets to see 2 eclipses in their lifetime. Pretty rare. It's very rare. Any one spot on Earth that you stand, it would take between 3 and 4 centuries for an eclipse to cross you. So these people right in here in that period of time, the 20-year-olds, they're kind of lucky. And the real lucky ones were the people that were down here in just south of St. Louis. This is about a 9,000 square mile area. You can see St. Louis here, and then Illinois is here, and this is the extreme western part of Kentucky. So they were covered with an eclipse in 7 years. And so that is extremely rare. They still have to pay taxes on April the 15th. It doesn't do anything magical for you. But again, that just kind of shows how rare some eclipses are. In any given year, you usually have 2 to 3 eclipses. There could be up to 5 on the planet. And again, going back to the serocycles here real quick. The serocycles have nothing to do whether, like the one here next Monday is here, and 18 years ago it was in Europe. The rotation of the Earth has nothing to do with the eclipse. It's just rotating underneath the shadow. So where's the Earth going to be in 18 years at that time? They just have to figure out the rotation. So those cycles have nothing to do. It's like, well, if it repeats, why doesn't it repeat here? Well, the Earth rotates underneath that shadow, and one has nothing to do with the other one. So now we'll talk about a little bit of the history. The eclipses have been used for a lot of changing history, but for different reasons. Back in the 585 BC, there was a battle between the Lydians and the Medes. They were fighting, and an eclipse happened. They were in the path of totality, and all of a sudden it got dark. And they had no idea what was going on. They had never been in an eclipse because, again, every 3 to 4 centuries they had never seen a total eclipse. And if you also remember back in 2017, unless you were looking at it, you probably didn't even know that 80% of the sun was blocked here for that eclipse. The light might look a little eerie. It kind of looked a little bit like maybe some of the fires that we had from California. The sun was dimmed a little bit, but unless you looked up and didn't know there was an eclipse, it wasn't real dark. But anyway, so there was a total eclipse. So they all stopped and they're looking around, and as soon as they stopped, 4 minutes later the sun came back out. So they thought, whoa, okay, that was a sign from the heavens, and it stopped the battle. They stopped fighting. There were, and in this slide too, there were a lot of, with Muhammad's birth during an eclipse, his son passed away during an eclipse. There was a lot of superstition and history there. So, fast forward a couple thousand years to, now this was the last eclipse that came across Ohio, mentioned in 1806, June the 5th and 6th, or June the 6th in 1806. And you look it up, it's called Tecumseh's eclipse. Back then, the Native American Indians, and I mean, there was still all the fighting for land and what belongs to whom and everything else. And they realized that, they never had to fight for their land or talk about treaties or anything like that. They had lived here, they were here all their life. We were the new kids on the block. And so they finally realized that they needed a seat at the table. Somebody has to listen to us. And so in Greenville, Ohio, there were some scientists that had come in that knew that there was going to be eclipse. Tecumseh and his brother caught word of this, and they were told, oh yeah, the sun will be darkened on this day or whatever. And so the governor of Ohio at that time, when Tecumseh, they went to said, hey, we want a seat at the table here. We want some negotiation rights. He said, well, who are you? What can you do? And so he threw the gauntlet down. He said, make something happen. Make it rain, do something, the sea part, something. He threw some stuff out there. He goes, well, how about I darken the sun on June the 6th? Yeah, go ahead and do that. Well, boom. So all of a sudden, history starts to change for another reason. Now, because you knew what an eclipse was, as opposed to when you didn't know what it was. So people started using them for other reasons.
Was that June 6th?
What's that?
Is that June 6th?
Yeah.
666.
Yeah. Well, yeah, there you go. The devil. Yeah, you're right. Yeah. So now, of course, we use eclipses. We know what they are. In 1919, an eclipse was used to predict or verify, I shouldn't say predict, verify one of Einstein's theory of relativity. Light particles have mass, and one of the theories of relativity that he had was that if a light particle passed by a large gravitational body, it would be bent. And again, you've probably seen the diagrams where space-time is bent, it's warped, it's like a fabric. Again, everything's relative to where you're looking at. And so what they did during the eclipse, and again, I'm going back to the fact that the moon is the same exact size as the sun, so to speak, in the sky. If it was bigger, you couldn't have done this. They knew, of course, where stars and everything were, and so they knew that there was going to be a star right at the limb of the sun, right at the edge of the sun, actually behind the sun. And they said, well, if Einstein's theory of relativity is correct, we should be able to see that star because the light will be bent around the sun. And they proved it in South America and in Africa from two different directions because they wanted to be sure that it wasn't a parallax issue. In other words, like back there, WCTV's back there. If I'm standing right here, the camera's to his left. If I'm over here, now the camera's to his right, to the right. So they wanted to be sure that it wasn't a parallax issue of why that star was visible, and it wasn't. So it was about an 80% proof that Einstein's theory of relativity was correct. Now this is more of a fun fact, but this isn't really Einstein's theory, but talking about looking at things from a perspective relative-wise. If you're in a car going down I-76 windows closed, obviously, and there's a fly in the car. Somebody says, how fast is that fly going? I can't answer that question unless I know who asked it. Okay, if you're in the car, the fly's not moving, is he? Unless he's flying from the front seat to the back seat. He's not moving. If he's sitting on the steering wheel, the fly's not moving. I get out of the car, he's moving 75 mile an hour. 65, you know, whatever. If Kate's driving at 75, I don't, no. But so, and then if I come off the surface of the Earth, and that's at the equator, the Earth's rotating at the equator 1,037 miles an hour. Now that fly's moving 1,037 miles an hour plus the 60 miles an hour. So everything's relative, and a lot of Einstein's theories were, again, that's not his theory, but again, it's an example of how you approach, if you're going very fast and you approach the speed of light, time actually slows down. So I'm getting out in the weeds on that a little bit, but again, that just, so we go from using the eclipses for very scientific purposes anyway. Well, okay, well, evidently I stopped talking long enough. Okay, and the pointers quit working here. So why is it, Chicken Little, why is the sky falling around the eclipse? Why all the hoopla and everything else? The path of the eclipse, again, that's it. Now, I'm not sure why they use these colors here because they're hard to see, but you could see where the most populated portion of the United States is right in the path of the eclipse. And the furthest band out here is an 8 to a 10 hour drive to the eclipse. So there's, what, 8 million people or whatever within a 10-mile drive. Now, you won't be able to do this next Monday, literally, because of traffic. But if you lived in Washington, D.C., it's 5.5 hours from the east side of D.C., west side of D.C. You could drive, you could leave at 6 o'clock in the morning, be here, eat lunch, watch the eclipse, and go home that night. It's a long day, but you could do it. So part of the influx of everything coming through here is the fact that the eclipse path is going through an extremely populated part of the United States. It's not hitting, Utah and some, a lot of the desert states. It's hitting populated areas. And especially with some of the people here that have been in the Akron area for a while, remember that Akron was the trucking capital of the United States, trucking capital of the world, so to speak, because 2/3 of the population of the United States were within a 24-hour drive of Akron, Ohio. It's the other reason people are, looking to come here because of the infrastructure. I-71, I-77, the airports, the turnpike. You can get to, and I'll show it on the next chart. You can get to this area right here in no time. And so everything's just being prepared for if somebody's coming to look for the eclipse. In Ohio, just in Ohio, there's 7.5 million people that live in the path of the eclipse. Well, add a few million, maybe a million more to that, but add several 100,000 to each city to that, and you could run into trouble. I know Lori's husband Roger was down and went down to the eclipse in 2017 in Tennessee. They had, again, there wasn't any looting or anything, but the National Guard was out there directing traffic. It took 10, 15 hours from certain areas to get out of town. The gas stations didn't have gasoline. It was just because everybody was in and out. Somebody did ask me at one of my other presentations, they heard that cell phone service will be affected. Well, it will, but not because of the eclipse, because there could be thousands of people in the area. That's why. It's no different when you come downtown for the 4th of July, for the fireworks. You can't call and order a donut. You can't call across the street. Yeah, phone service will be affected, but not because of anything magnetic or anything that happens with the eclipse. It's going to be the fact that there's a bunch of people around where a lot of the towers are. So all right, well, I guess let's jump down here. So again, what we see right here is of course, Texas is a long state and it goes through some of the bigger cities, but if you look right here, Ohio, Pennsylvania, Indiana, and Illinois, there's why the sky is falling around here. Because this area right here, because of the infrastructure that I talked about, are the areas where everybody's going to travel to. All the populated areas here along the coast, you know, from Baltimore all the way down, 90 degrees, of course, is your shortest route. You're not going to go down here to see the eclipse. You're going to go the shortest route. Look where that is. Illinois, Ohio, Pennsylvania, New York. So that's why some of the areas around here, you hear a lot more people coming in. Well, and the same thing on the other side. You know, I keep talking about the East Coast, Chicago and everything else. I mean, Chicago's a day trip if you want to go up there to one of the museums. I mean, you could drive to Chicago and come, you know, from Chicago and watch the eclipse, cross the turnpike and go home. So that's the other reason that this area here is looking, you know, they were looking to get hit a little bit harder. This is a little estimate of some of the numbers I just talked about here in Ohio. These are the numbers here for Wadsworth. The partial eclipse at 1:58:46. Totality at the 3:13:49. The maximum eclipse, they're 3:15, 2 minutes and 58 seconds. It ends at 3:16:47, and the entire eclipse ends at 4:28. So it's about you know, from roughly 2 o'clock to 4:30 is what is the time of the eclipse here in Wadsworth. Now this here is a neat little. If it works, come on, load up here. A little example of the eclipse here. Let's see, I even brought my own internet so this wouldn't happen. Let it load up here a second. Oh, there we go. Thank you. Okay, so what we have here is there we go. Let me zoom out here. This actually did not load right. Hold on here. Let me back out of this because, there, now it loaded. All right, there we go. I was going to say that did not look like anything. All right. So what we've got here is this is showing now we got it. All right. I knew I'd get there eventually. Let me turn off the cities. So this is going to show how the eclipse is coming across the Earth, okay? So the little dark purple here, that's the path of totality. And you can see how that's coming across the United States. The entire width here is the area of the partial eclipse. And you can see like this out here, that's the 50% line, 75%, and then the total part. So that's the effect on the whole planet that the eclipse will have. Or it'll go all the way up. And then if you look behind the moon, a visual here from behind the moon, there's how the shadow, you can kind of see it, that dark band right there. But again, the sun's coming over this way, and you can see the focus point. Again, because the moon is the same exact size as the sun, that focus point is almost, you know, like a needle in. So back out of that. But anyway, little example there of that. Get that closed there. Now there is a site out there too where you can figure where you're going to be and what the totality is. You know, where I figured here in Wadsworth, right in here, you know, we had that 3 minutes. Well, if you go down here toward, I actually did one out at the village of St. Edward and Green. If you come out here, right next to, let's see, they were roughly right here. You come in here, see, they had 1 minute and 3 seconds out there. And so in the eclipse, if anyone's traveling anywhere, if you see that path, you don't want to go along the path, you want to go 90 degrees to the path. In other words, you want to If you're you're going down toward Columbus or whatever, you don't want to go a little bit north. You want to go northwest. You want to get toward the center, because the time along here is the same. I mean, Wadsworth has 3 minutes. You come down here, Paducah, Kentucky has 3 minutes. So you need to go more toward the center if you're trying to get anything a little bit longer. So again, this just showing some of the times here. Again, there's Akron. There's a little dip in I-76 you see, and so 3 minute line. There's Wadsworth right there. So I told you how because of the moon being so exact size of the sun and the curvature of the earth, as you go up the earth, you're getting further and further. You're outrunning the sun, so it's getting smaller. So you see right here down in just south of south of Wapakoneta, you've got 3 minutes and 58 seconds. By the time you get up to Lake Erie, you're at 3 minutes 52 seconds. So you're 6 seconds difference in just that little area there. The shadow's moving about 2,000 miles an hour. So again, when you look at the whole planet, I mean, that right there, for all the people that believe that the earth is flat, that right there just proved it's not. But so that's why some of the times vary like that. This here is a neat little example here of, do a full screen here, of why there's so many different times. In other words, why out to the edge it's less than a minute, and why in the middle it's not. Well, this here is an illustration of, now this is following the path. So right now we're over in Indiana, all right? We're in Indiana. And this is how the path of the eclipse goes across our area. So you can see, if you're out here, you're only in that path for a short period of time. Here, you're in it for a longer period of time. That's, again, it's really not rocket science. It's the fact that it's round. You're hitting the outside of the basketball. And so everybody out here is, very small amount of time, and then in the middle, you're in it the longest. And you can see the speed of the shadows that's going across there. And again, you see it's increasing. 21, 20. It's increasing. It's falling off the round part of the earth, because again, as you change that flashlight, that thing takes off quicker. And so that's why the speed of the shadow is picking up. And again, that's why the time ends up changing. Got that. Okay, so here in Wadsworth, what this is going to do is, this is a demonstration of what the eclipse will look like here. So the sun will be, it'll be just under 60, about 55 degrees up in the air. But what we'll do here is, come on here, there we go. All right, so as you're looking out toward the south at the sun, the eclipse is going to start about the 5 o'clock position. See it coming on down there at the bottom? So it's going to start there. It's going to come up. It's going to take a bite out of it like that. And then totality there at the 3:13:47. I'll talk about some of this here in a minute too, and I'm going to stop right there. The 2017 eclipse was at the low point of the sun's solar magnetic cycle. Okay, 6 years later, it's about 11-year cycle. 6 years later, we're in the middle of it now, and solar flares have really picked up lately. So they're telling everybody to look. Now you'll need optic. You're not going to. If you see one with your eye, we're not. It's Armageddon. We're not going to be here. But with some optics, again, you have a very good chance of seeing activity here on the surface of the sun, the solar flares. Again, because of that, and that wasn't as visible or visible at all in 2017. Again, the other aspect of the moon being the same size as the sun. If it was a lot bigger, if we were a lot closer, look, you wouldn't even see that. And you see here too, in this, I can make it a little bit darker. You see the light glowing around, oh, I'm sorry, here, I should use it. I should use what the software did here and it would quit jumping like that. Okay, so the solar corona, nice clear day or whatever, you're going to see the corona, all the light go, the corona of the sun going out behind the moon. Again, if the moon was larger, you wouldn't see that. It would all be blocked. So the fact that the moon is, again, I mentioned that earlier, it's just so many unique opportunities in an eclipse. So then, after totality, it's going to come up, it's going to stop from the bottom again, around the 6 o'clock position, and go up and then be done just 11 o'clock-ish. So that's the path that it will take here in Wadsworth, from the 5 o'clock to about the 11 o'clock position. Now, some of the things that happened during the eclipse there we go, yeah. At about 15 minutes before, you'll really start to see everything get dark. You're really going to start to notice it. And then at 10 minutes before happened, everything, the shadows become, the sun is a big light box. It's like putting a big sheet up and lighting everything. But as the moon starts to cover the sun, it starts to get a pinpoint of light. Shadows get very, very sharp. You can, and then especially at that part of the eclipse, and even during the partial eclipse, you can do some neat things with, if you have a colander that you drain noodles with, you hold that up, and as the sun shines through that, you'll see like 500 little eclipses on the ground. It makes a pinhole camera. And again, that you can't see even a round sun like that, because when it's round, or when it's not an eclipse, again, the light is spread out. But during an eclipse, it starts to get pinpointed, and it functions like a camera. So what you'll, and then about 30 seconds before, darkness is, it's just going, that last 30 seconds, it's going to come on very quickly. Temperatures, maybe not because it's April, although right now it's supposed to be 60 degrees and sunny. On a nice warm day, temperatures will drop 10 to 15 degrees. It just, where at night, and of course at night it does that too, but it's gradual. This happens immediately. So and again, we're not going to have any flowers out now, but flowers that close up real quick, they'll close up because they think it's nighttime. If you're out in the country, and you can if you turn a recorder on, afterwards you can listen to the eclipse, because all the birds, all the crickets, and you'll be able to hear the sound difference. And I've gotten some audio from people that have done that, and when you look at audio, you see the waves, you can see the exact change in the audible area of the planet when an eclipse happens. It's just neat. The other thing that happens right at the eclipse is you'll see this diamond ring effect. There'll be a real bright spot right before the sun covers everything. And then the neatest thing is called Bailey's beads. Let me jump up. Now, what Bailey's beads are, of course, all the little bright, tiny little pinpoints of light. What that is the surface of the moon isn't smooth. It's mountains and hills and valleys. That is the sunlight peaking between the mountains and the valleys on the moon. And again, because it's pinpoints of light, the little flicker and everything else as you come through there. So that is, so you'll see Bailey's beads. You'll see that at just before totality, and then you'll also see them on the opposite limb when the sun comes off. So you'll have an opportunity to see those twice. Again, during totality, talk about this a little bit when we talk about how to watch it. Take your glasses off. Take your glasses off. I mean, number one, you won't see anything with them on because it's dark. But 100% safe to take your glasses off during the eclipse. If anybody's going to be in a group, if you're at a church or something like that, and you're with a bunch of people, one thing that's good to do with all the people is The atomic phone apps, atomic time, exact, National Institute of Standard Time. You watch it on your phone, and again, because of where you're at, give it a few extra seconds. Right at 3:13:47, don't blow the whistle. Give it a few extra seconds. But you blow the whistle, and then everybody in the group knows to take their glasses off. I mean, that's just a lot of the big groups do that, and at about 5 or 10 seconds before, blow them, so everybody puts them back on. And again, that's just just a way to do that. And the same thing there, as the eclipse stops, birds will start chirping, roosters will start crowing again because they think that it's sunrise again. So one of the really neat things here that you'll get to witness and you can see the sun is right there. Jupiter, Venus, Saturn, and Mars will all be visible.
Wow.
So when you're looking at the sky, to the upper left of the sun is Jupiter, Venus, and then Saturn and Mars are real close. You'll get to see 4 planets during the day. So again, right, and again, they're not visible now during the day because they're next to the sun in their normal orbits around, not physically close to the sun, but just in their orbits around the solar system. But you'll get to see those planets during the day. Now I'm sorry, that's a cool picture right there. If anybody we're going to capture that, the sun and the planets right there. This here was the eclipse back in 2017. As a matter of fact, Kate was out there with me. Thank you. Kate was. We were out there looking at the telescopes with this. This was the maximum that we saw. So you've got 70-ish% coverage right there, and we were as far away as Nashville. I mean, the 90-degree line was roughly Nashville. So we're that far away from the total eclipse, and that much of the sun was covered here. So this is where it started. You see how it came across, and this is what how the sun came off of it. Again, there in 2017. What's really neat is if you do have a telescope, binoculars, or something like that, and there's sunspots out. This is a sunspot. I took this at the 2017 eclipse. You have no idea how fast the moon is moving unless there's something relative there, and it gobbled that up in 30 seconds. I mean, you could see it moving. It was. I mean, you did a double take. I mean, you're thinking there's something goofy or something wrong, but you could really see it moving. Sometimes you can see that on the horns up here of the moon, like when they're real thin. Sometimes you can see that point change relatively quick in the sky. But if there's a sunspot there, I mean, you can really see that. You can really tell that couple thousand mile an hour movement. The other thing that's neat during the eclipse is a lot of people of my age or whatever that owned AM radios in the day. The transistors. You know that at night, when the ionosphere is not charged by the sun any longer, AM radio waves bounce. And so you could pick up stations from way, way, way far away. So they do studies to analyze what the atmosphere does during an eclipse. So there's a list of radio stations out there in the path, and there will be people monitoring all along the eclipse to see if they could pick those up and how the ionosphere drops in charge during those couple minutes. Well, and actually it's not just total, but even going on and going off, and again to analyze some of the effects on the atmosphere that the eclipse has. Shadow bands form right before totality and right after, again, when you get those pinpoints of light. This happens on, you'll see it, you won't see it on like if you're outside the library, the brick. You need a nice smooth, preferably a white surface. And what it is it's easy way, or a cheap way of explaining is like you've been out in the summertime and you see the heat waves kind of coming off the asphalt or whatever. Well, in the upper atmosphere, because of the quick cooling, depending upon how hot certain layers might be, it gets cooled real quick. So all of a sudden those layers start moving it around, and it creates the ripple effect here on Earth. Now, and again, it's a very local, it can be a very local effect depending upon the weather. You might see it here. If you're down at the bottom of College Street, you might not see it. It's like, well, you know, what are you drinking? I didn't see that. But it was, it can be a very local effect, but you need preferably a white or a very small, a smooth surface. I mean, if you have a piece of, you know, cardboard or, you know, poster board or whatever, take it out. And if you happen to see them, that's what's causing that. Again, it's that pinpoint of light shining, going through the atmosphere.
Do you lay your white, like, lay it down, or do you want it up?
Either. You'll see them on the ground too. You can lay them on the ground because it's coming down. You can see them either way. Yeah. Now we'll talk about looking at the eclipse here a little bit. Anything that you look at the eclipse with, your filter needs to be on the business end of that. Whether it's your eye, the telescope, a pair of binoculars. I mean, the one thing that you don't want to do is put your glasses on and do this. Okay. No. You have to have some filter out here. Will this work? Yeah, as long as your glasses don't get burnt by something. I mean, everybody's fried an ant with a magnifying glass, depending upon, and of course, when these are close to your eye, that's not happening. But as you approach your eye with it, that focus point is out here. Whereas you get close to your eye with it, I'm not saying, I mean, there's just a chance of something happening. Just don't do it. Just like on the telescope over here, and any telescope or whatever, or camera lens or whatever, your filter needs to be out here on the business end. The light from the eclipse has to go through that filter first. Again, except during the eclipse, take your glasses off. All bets are off during the eclipse. Again, totally safe to do that. The other things that do not work that in the past people have, you know, you cannot use CDs. People use them as sunglasses and Mylar. All of the sunglasses are Mylar. Okay, well, so is that potato chip bag. Doesn't work. Okay, people, you know, a lot of blind people have tried that. And so those things, they just do not work. I mean, and again, you could take that potato chip bag and you can hold it up to light. Wow, I can barely see that light bulb through that. Yeah, and it's also not filtering out the ultraviolet rays and things like that too. So no homemade eclipse filters. A couple of things you can do too. Now, the sun going through a telescope or through a binocular or whatever isn't unsafe. The binoculars might heat up a little bit, but it's not. Nothing's going to happen. You can watch the eclipse that way. It looks really nice and easy and fun in that picture. It's not, because the sun's always moving, and you can't get down there and look at it to line it up in there. Again, but if you have a big group and a lot of kids or whatever, I mean, you can do that. Nothing wrong with it. Absolutely nothing wrong with it. And the only thing they did down here in this picture is they put a piece of paper around it just to make this darker. That's all. That's all that is. And again, for a big group, that's fine. That's one thing. But to me, that's like watching somebody else fish on Saturday afternoon on TV. Just get a pair of turn around and look at it. If you get a pair of glasses, don't miss it. Don't miss it. I mean, I mean, that can be done. You can do that, but again, there's nothing wrong with that sunlight passing through equipment like that. The other fun thing to do for the kids is, bottom line is what they did is they made a welding helmet, because a lot of people were talking about, and I found this, couple of people said, well, I'm kind of worried about my kids. You know, the glasses aren't that big, and they're looking up, and the brother's going to hit the, you know, that kind of a thing. That's like, well, if you basically make a welding hood out of for them, I mean, if you know they've got the glasses go through the plate, and if anything moves around, they're not looking at the sun. So it's kind of a fun thing, you know, for the kids to do, and you know, you can make fun of them on their wedding day when you put those up there. Going back to some of the equipment or to watch the eclipse. Again, you've got the solar glasses. Welding glasses. We were talking earlier. Welding glass is 100% safe. 100% safe to look at the eclipse with. Number 14 welding glass, okay? There are other welding glasses out there. Some of them have a little bit of a tint to them. If you're a MIG or a TIG welder, those glasses are like number 11 or number 12. They're a little bit lighter. An arc welding glass is number 14. So if, even like a welding helmet, you put this in a welding helmet, you can look up. And the other thing you don't do is look up and then put this up. You got to do it that way. But again, welding glass, perfectly safe to do that with. And then let's see. On the other hand, here, let me jump back real quick here on. A little interesting, going back to history here for a second. Of course, we just had Easter. Last Friday was Good Friday. Pick up a Bible, especially in Luke, if you're using the Bible for historic references. Luke says that the sun was darkened from 12 o'clock to 3 o'clock by an eclipse. Wrong. It wasn't. It was not. There was no eclipse on that day. And so you start to going back. He goes, well, it says so in the Bible. You go back and study, there were no eclipses on that day. Number one, Passover, that was Passover weekend. Passover's on a full moon. Wrong side of the earth, okay, for the moon. And so you start to go back and look. Well, if you go back to the original Bible verse, it doesn't say eclipse. That was in a translation. Somebody decided it was an eclipse. And again, once you write it down, it changes history. So when a lot of research gets done on, you go back and look at tablets or things like that, you really have to look at when it was written and who wrote it. Again, just like being in the car, how fast is the fly going? Well, I gotta know who's asking. And it's the same thing with the eclipse on Good Friday. Now, also in all the Gospels, it talked about on Friday night, after the crucifixion, there was a blood red moon. Well, what is that? Everybody thinks that's an eclipse, and it's like, well, okay. So you go back and you start looking scientifically. It's like, well, if something darkened the moon or darkened the sun, it could have turned the moon red that night too. I mean, it could have been a fire somewhere. It could have been, a volcano. Those kind of things. It was something that was in the sky. But during Pontius Pilate's reign, there was one eclipse. It was on April the 3rd, that night. So again, other things point to, yes, there was an eclipse of the moon that night, but not an eclipse of the sun. So that was one of the strongest, and there were several other historical things that pointed to it. But the Good Friday, the crucifixion, has been narrowed down to April the 3rd, the year 33 AD. And the eclipse of the moon had an awful lot to do with that because it was referenced, a blood red moon, and that was the only eclipse that was visible during Pontius Pilate's reign and visible in Jerusalem. But again, no solar eclipse whatsoever on Good Friday. That did not happen. And again, darkened for 3 hours, darkened for 3 minutes maybe. And again, you wouldn't notice it. So something else, if it was, whether anyone wants to believe it was supernatural or just a storm. I mean, it could have just been a horrible storm that came in off the Mediterranean, and it lasted better part of the afternoon. So yeah, there was no eclipse on Good Friday. One other thing that scientifically that was proven, because the moon, again, I'm going back to that, is the same exact size of the sun. Everybody knows spectrum, how light is dispersed and everything else. Well, because of the pinpoint of light, they were analyzing light from the sun. The element helium was discovered during an eclipse before it was discovered on Earth. Helium, that's what the sun burns, helium, but it was discovered on the sun before it was discovered on Earth because of that pinpoint of light. They analyzed it with a spectrograph, and so it was, so again, if the sun was a lot bigger, none of that would have ever happened. So again, that uniqueness is there. So before maybe I jump into a little bit on some of the equipment, any questions on anything?
I did hear on trying to use your camera to take a picture, like your iPhone or whatever, to take a picture because it's going to be bad for your camera. So don't do that.
It can mess your lens up. It can. Now during totality, no. Again,
Okay,
if you
good.
right during totality, you're fine. And on your iPhone,
You could get some of that.
I mean on your phone cameras are small enough. Heck, you can put it. I mean, you can put one of the glass filters over it. This is fine. Absolutely. Yeah. Because you can. You could hurt. You could burn the photo cell or whatever that's in the camera like that. Yeah. You're better off. You're better off to cover it with something.
Okay.
Yep. So if no other questions, I can talk a little bit about some of the different kind of telescopes here. The three main telescopes: refracting, reflecting, and the like the one over there, the catadioptic. The refracting telescopes are the ones that were out from day one, Galileo and everyone else. They are, they have a lens like this at the end, and it comes back and focuses. You put an eyepiece in, and they're and again, just like with almost anything else, there's some better, some worse, but no real. What should I go by? In other words, if somebody's in here is going, okay, whether it's you, whether you've got a grandson or a brother, sister, anything like that, what should I buy him? A refracting telescope is fine. I know Roger wants to win the telescope over there. That's the telescope we're giving away at the radio station. We're raffling that off. Solar filters and all to be ready to go out and watch the eclipse. Roger wants to use that to look at varmints out in the woods. Roger's going to see all those varmints, but they're going to be upside down and backwards, because that's what telescopes do. For example, even a refracting telescope will, and I can probably, if you'll hold that close, hold it or close to your eye, and you can see, it's not even blurred, but you can see it's right side up, right? Yeah. Now watch. Now watch it. Flip, yeah.
Yeah.
Upside down. It's upside down now because the way light goes through this, it comes through here, it's refracted down, it comes through here, it's refracted up. So that point where the image flipped is where the light flips in this lens. Okay? So that's what a refracting telescope does. You can correct that with the prism there at the end. Binoculars are refracting telescopes. Why don't they flip the image? Because they've got a prism built into them that flips it back. Refracting telescopes they're excellent for looking at stars, planets, things like that. Anytime light goes through glass, it's Pink Floyd made the Dark Side of the Moon album for a reason, with the spectrum. Anytime it goes through glass, you get chromatic aberration. The light is split into colors. You can correct that with coatings, and you can put another lens over here and another lens over here and have it go through 3 or 4 to try and bend everything back. Now you've quadrupled the cost of that telescope. So, and again, for most people, if you go out and I don't mean to scare anybody with numbers here, you go out and spend $400 or $500 on a refracting telescope, you're going to be fine. I mean, a lot of the really cheap $49.95 ones, if you can find them at the dollar store or whatever, they're really going to be a mess. Then when reflecting telescopes came up, they have mirrors in, and there is no chromatic aberration in a mirror because light doesn't pass through a glass. So what you have is the light comes in straight into the tube. There's a mirror here, focuses, it sends light to here and then up to the eyepiece. A lot of, again, the Mount Palomar, a lot of telescopes are reflecting telescopes.
Was it Comet Cahootech around 85 or 86?
Mm-hmm.
I bought a telescope when kids were young, and it turned out to be the biggest dud.
Yeah. That was I think it was Cahootech at that point. Yeah, but it was supposed to be this big, humongous thing in the sky. Yeah, Hale Bopp was the other one in what was that, 90, I'm trying to remember the 90s or whatever. You could see a tail on it. I mean, it wasn't too terribly bad, but
Better than Kahuta.
yeah, oh yeah, yeah. But
What's the value of the one that's going to be?
$1,000, $980, I rounded up, $1,000, because that will also, that's also the solar filter, and I have the glass solar filter on that one, not the Mylar. But again, reflecting telescopes, you'll see a lot of those, and you know, downside to that is if you have a reflecting telescope down here, look where the eyepiece is. If that thing's here, the eyepiece is up here, so you're usually up on a chair or a stand or something like that doing it. The ones on the bottom is like that one over there. It's a Schmidt-Cassegrain, and what these telescopes do is you do have a corrector plate that takes not the chromatic aberration, but just aberration of light. It kind of polarizes the light and kind of straightens everything up, so to speak. So everything hits the mirror straight. So you have a mirror back here, comes up on a mirror here, and then goes straight through to the eyepiece. Now, those folded optics, you've got a length here, a length here, and a length here. That telescope right there is the same thing as a close to a 60-inch long refractor. Okay, the optics are folded on. It's nice in a tube. It's all closed up. That's the other disadvantage to a reflecting telescope. Everything's wide open in there. And if the mirror gets dirty, how you get? I mean, it takes a lot to get to it. Refracting telescope lenses are easy to clean. The tubes are sealed up for the most part. I mean, where you put your eyepiece in, they're not, but not a lot of stuff's going to get up in there. The optics on that, I mean, if you take the back off, I mean, you can get in there to them. But it's not, and they're not the be-all and end-all either. I mean, if you're a purist and you're really doing some more high-end astrophotography or something like that, sometimes, especially with the planets, sometimes a refracting telescope is better. You do lose, you'll lose about, in other words, an 8-inch telescope like that would be about the same as a 5.5 or 6-inch refractor. You're losing a couple of inches, roughly, and that has a lot to do with the light gathering power, because you have this, maybe I can turn this around here so everybody can see it. You have in this telescope here, oh, what am I doing here? See there in the middle? That's that mirror. So what that mirror is doing is not letting light in there. Now, when you look through this, you don't see a dot there because the other mirrors in there take care of that. But as far as light gathering power, a refractor has a little bit more light gathering power than that. But like for example, the largest refracting telescope still in existence is in Wisconsin, Yerkes Observatory. It's a 40-inch diameter lens like this. Now, here, can you imagine? No, seriously, I mean, here, 40-inch diameter precision ground lens like that. I mean, and again, the support of it. When it's up like this, it's one thing. When it's in an angle, I mean, there's always all kind of different forces and everything else on it. So huge telescopes are just very impractical to make refractors. They cost too much. You can't support the mirrors. That's why Hubble and a lot of the other telescopes, the Webb telescope, they're mirrors. They're small mirrors, because you can make a very precise mirror very small, and you can make a lot of them, and you just put them all together. And you can support the back of them because the light doesn't go through them. So that's why a lot of, whether it's a reflecting telescope or especially the newer design here, they're a little bit better along those lines, because you don't have some of those some of those other support issues. You can get a lot larger A lot larger mirror and lens and everything in there. Now these, I'll tell you what, the one I'm going to show you here in a minute that I own, I've had the thing for 10 years and I've never had to do any adjusting on it. I mean, if you read up, it says that there's a lot of extra culmination that has to go on the lenses or whatever right here. Well, unless you throw the thing down the side of a mountain, you're not going to have to mess with the lenses. I have the refractor that I got as a kid when I was in 1969. I've never touched, I mean, other than cleaning, I've never touched the lens on that thing. So, I mean, so some of that when you read it, unless you're hard on equipment or something extra happens to it, you're not going to run into that. Now, this is what I was showing you right here. That point of where the image changes right there, he was able to see that. Everything was right side up, and as I got out there, the image flipped. And so and again, that's what, this is just some close-ups of what the different telescopes, how they bounce the mirrors. And you see back here, other than this being an obstruction, as you come back through here, you have the light passes through that back mirror. So you don't have anything on here picking up light, but you wouldn't anyway because you have this other mirror here in the front. These telescopes can also, and for the average person like even me, this isn't going to matter. Sometimes, again, if you're doing astrophotography, it's like when you do a selfie, you see everything's kind of distorted. Well, a telescope like this, out on the edge, if you're doing some wide field photography, it can distort a little bit of the stars. Are you going to notice it? No. But if you're doing scientific work, it can. So what they can do in this design, this mirror up here, they can change that to correct the flatness. So that where that can't be done in other designs, it can be done in this design. So there's just a lot of things that, you know, with that type of a design, and again, they're out there. I mean, you could, again, not that it's cheaper than a bass boat, but you know, for $1,000, yeah, and even a lot less than that. I mean, you can get that telescope. But again, that telescope there too is computer controlled. I mean, it's you can go out and line it up with the stars and tell it to go find Saturn, and it will do that. There's one thing though, if you're looking at a telescope, what I would recommend is, like during the day, if you go to have this thing follow the sun during the day, you know, the alignment on this thing, there's no stars up there to look at. So if you buy either an equatorial mount or you buy a polar mount, you set this at 41 degrees, which is our latitude, all right? Now, point this north, pretend that's north, right here. Just pretend that's pointing north. This right here is parallel with the axis of the Earth, okay? So when this, if I just start the motor up, now what that's doing is that is emulating the rotation of the Earth. So this, not at this speed, but when the tracking is on, this thing rotates at the speed of the Earth, and it will follow the object. And so that quickly, now, yeah, in 20 minutes you may have to bump it back in, but it's one of those things where all the technology in here is really great. And it's like, oh, it'll tell you, go find this star, center it in, hit. Well, there's 3 bright stars out there. If you don't know what you're looking at, and again, if you don't know what you're looking at, this thing is upside down and backwards. So you're looking at a map, you're looking at it in a mirror. I mean, I'm not poo-pooing the technology. It's great, but I'm just trying to make it practical. You end up with a mount, with a polar mount, and again, you know, ballpark it toward the north. Put a compass down there and ballpark it toward the north. Put this on 41 degrees, and it will track something from sunrise to sunset. A lot easier to do that way. And a regular equatorial mount is, let me come over here with this one, is like this. This obviously I have this camera lens on here. This is a camera mount here too. But what this does is, this is the same thing. If I tilt this axis parallel to the Earth, 41, whatever your latitude is, wherever you're at, 41, all right? I do that, and then this is emulating the rotation of the Earth. So I've got a little motor on this. I point this north, turn this motor on. This thing here will follow just like that. With this one simple motor will follow the sun or a star or the moon in the sky. Very simple. Didn't have to go through all the computer or whatever. And again, the computer is great. I've used it. It's fine. I mean, you can do different alignments with it. I'm not saying it's a bad thing. I'm just saying if you're going out there and looking for something, and unfortunately they get really proud of a mount. It looks like very simple, but I think the tripod was like $400, and it gets kind of silly. But again, those are the things that all of a sudden make that usable, and it's like I just get frustrated, and every time I go out I can't get it to work and it sits. So I'm not saying you spend an extra $300 on something to get somebody to use it, but what I'm saying is those are some of the things to look for if you're buying something like that can make it more usable. So what do we got here? Okay, so on any telescope like that, if you have a camera where the lens comes off, any removable lens camera, you can buy an adapter. Okay, this goes on. This has the same mount as a camera does. This goes on your camera. This goes in the eyepiece. That telescope becomes your camera lens. So on the little picture that I have here where we're doing the raffle, the picture of the sun on there that I took, that was with that setup right there. Just that becomes your camera lens. And again, that's if you have a DSLR or anything where the lens comes off, that you pick up that little adapter right there, and I mean you're off and running. Now on a telescope like that, you're not going to take a 3-hour time exposure. Now you'll take now that's my other toy. That's an 8-inch. Schmidt-Cassegrain telescope, and if I'm standing next to that with it in that position right there, the business end is about here. So that's about how big it is. And again, that's an 8-inch. And again, what this is the wedge on there that thing right now is set at 41 degrees for Wadsworth, and again, we'll follow the rotation of weather. I point that thing north and start the motor, and it'll follow it. I don't have.
Country?
Huh?
Live out the country?
I don't. No, I live on Highland. Yeah, but that's that's the other end of it. And again, they call that a portable telescope. I have 2 telescopes very similar to that I do use more often. A lot of times, if anybody's been out to the Friends of Wadsworth Trail, some of the moonwalks, I've had telescopes out there. I've had that one out. There. But if you're not sure about rain or weather or something like that, if you're going to get it in, I mean, by the time you haul that one out there, again, it's called portable, but so is a refrigerator, I guess. You can move it, but that's the other thing when you look to buy something. Like for example, even on this one here, this comes, and again, I won't go through unscrewing it right now, but this one here will come off of the tripod, but I'll also show you here, this comes off. So you could take this and these legs here, and if you're going out camping, or set it on a table. So there's plenty of telescopes out there that are like that. And again, as far as transportation, if you don't want to just roll this up and fold it up, that's it right there. I mean, so you consider all those kind of things when you're buying equipment. And again, this is and again, the reason I picked this one for the raffle, it's kind of the best of all worlds. It's portable. It'll follow the stars. It's got the other mount on. It's a solar filter. It's kind of a catch-all. So and again, but just like with anything else, everything isn't perfect for everybody. But so that's some of the things on the equipment there. Let me.
So the body wins that? Does it come with like 6 hours of your time?
Oh yeah,
On
Yeah, yeah. So, but now, and again, science-wise, some of the other things. Now, this here, that is the planet Venus crossing the surface of the sun. I took this picture back in 2012. I think that I don't. I'm making this number up. It's like 2250 or whatever the next time it's going to happen. But I wanted to get it. It was cloudy all day. That was right before sunset. That was taking about 8 o'clock at night in June, and it cleared up enough for me to take. So that's Venus. Those are sunspots and clouds or whatever. But again, even in the past, as the planets pass across the surface of the sun, if you get in a location where it's right in the middle, science can be done as far as timing and size of planets and orbital information, everything else. This is a photograph that I just threw in for fun. That is the International Space Station crossing the surface of the sun. I took that photograph up in Medina 2 years ago. There's a site you can get on, when's the International Space Station across the surface of the sun. Yeah, it is. Yeah, you can see the panels and everything else on it. That was less than 0.7 of a second. It's like, it's quick. And again, because the sun, you always see big pictures of the sun, but you get your glasses tonight, go out, and the next time you see the sun, it's not that big. Visually, it's not that big in the sky. And but the camera that I have takes 15 frames a second. And so it's an exact time thing. It's just like the eclipse. Down to the 10th of a second when it's going to happen. So 3 seconds before you hit the button, I didn't know what I got till I got home. And there were 8 pictures that I could have gotten in that time frame, and I got 7 of them. That is a stacked photograph. That is all 7 photographs stacked over top of each other. But the camera didn't move or anything like that, so I put them over. And I was able. This is up by Lake Medina, right off of Route 18, and right there. it came across almost right in the center of the sun, the longest passage. If you're off center or whatever, you might only get 1 or 2, and it's less than 0.2 of a second. It's very difficult to catch it like that. But that's now. And again, I'm babbling here, but I'll jump back to equipment. I took that with this lens, and I had I had an adapter on it, a 2-power adapter that made this a 1200 millimeter lens. But I didn't have some big camera equipment that I did that with. I took that with my camera mounted on this lens on a heavier tripod, But
we've all been to the ocean or something. We see get up early in the morning to watch the sunrise or the sunset. If there was an eclipse that would be timed with sunrise, looking out over the ocean, because the sun's appears to be a lot larger at that time than it's when directly.
Yeah. Same effect. It looks larger.
I never remember seeing pictures or photos.
Yeah, and again, that's where you need to be in the North Atlantic or the South Pacific where it starts. Yeah, there are some eclipse. And that one, I'm sorry. That's Augie. That's my dog. That's Augie. Yeah, he had his glasses on. But if you go back to, let's see, if we run back to, what was I thinking of here? Where you would see it at sunset would be
Los Angeles.
If we go back to the one more slide, 2 more there. Okay, so right here, that's at sunset. So in 2044, if you head up there to North Dakota, it would be you would see it at sunset. You're not on the ocean, and again, that's the same effect that the moon looks. Sometimes it looks bigger because there's something relative, right? Just like those sunspots when it's eating it up, there's something there, so it looks bigger. But but that's and so that's. Oh, sorry, that's. No, I jumped out of the whole thing there, didn't I? But yeah, that was. I think I did go through everything here. One more here, sun and Augie, yeah. But and again, like I said, the with the telescope or whatever, the filter everything comes on there. There are some, and I found this out during one of the other presentations too. Somebody had, and I owned one of these, the very first refractor I had one of these, where they gave you a moon filter and a sun filter, okay? All your filters fit, they thread into your eyepiece, okay? Way back then, they gave you a sun filter. The sun filter went on your eyepiece, and you looked at the sun through here. And can you imagine what that did? Yeah, comes through here, and even back then I knew not to do that. It wasn't a good idea, but that's what they did. That's how they made them, and you know they were safe enough. I had a what they had back then too, and you get some of the older telescopes, you'll see this as well. This prism that's back here, what they did on it, they opened it up. There was a hole in it. It was called a Herschel wedge, and it let most of the sunlight through and just a little bit out the eyepiece. That was probably okay to use with the eyepiece like that, but I had that on, and I had it. I never used that filter. I wasn't even that dumb, but I was using it like projecting it on a screen, cracked my eyepiece. Cracked my eyepiece. So, and again, I wasn't dumb enough to be looking through it, but just the heat of that coming through, and where the focus point was, because you want it focused in the eyepiece to show up right, it fried that eyepiece, just like you cook an ant with a magnifying glass. That's a magnifying glass. That's what it did. So there are some telescopes back there that people may have had as kids, or you give somebody. Don't, just because it came with the telescope, don't use it. All of the, even on that telescope now, that's a smaller one. That's what this filter is off of. I use that one for that telescope, but as well. So again, always has to be on, everything has to be on the business end. So, any other questions? Anything? No?
Great job.
Well, thank you. Thank you. Oh, thank you. Well, thank you. All right. Well, thank you. All right. Appreciate everybody coming out.
You are watching WCTV, Wadsworth Community Television.